Okay guys, let's start the lecture. So we'll finish the pole placement today, okay? Just a quick recap of what the pole placement is. Okay, so here is a model of the discretized open loop system, the plant. Now, what we want is we want to place our poles of the system at the locations lambda 1, lambda 2, lambda n. Which means what we really want is we want a closed loop characteristic equation, which is this one here. Okay. So how do we achieve that? We achieve that by using a feedback u equal to negative k u x of k here. So we achieve that by using the feedback. And the only manipulable parameter here is this matrix k. So the k needs to be calculated such that the closed loop characteristic equation or the closed loop pole location is here, right? Yeah. The first method that we learned is for very simple system, or basically for low order system, such as a G, for example, G is a 2 by 2 matrix. Okay. So you can use hand calculation. Okay, so if this is a simple system, you can hand calculate. But if the G is relatively more complicated, let's say order of 3 or 4, okay, so I would recommend to use a formula. And the formula we learned in the last lecture is Ackermann's formula. Okay. So Ackermann's formula, I didn't give you the proof. You can take a look at the lecture note, the textbook for formal proof there. So the k equal to 0, 0, 0, 1 multiplied by inverse, okay, of the controllability matrix, okay, multiplied by the inverse controllability matrix, and then multiplied by alpha Cg. So what is alpha Cg? Alpha Cg is this is the desired polynomial here, so we call that alpha C. Okay. So we replace this one of the z here with the g, so that's alpha Cg here, right? Yeah. So alpha Cg is g to the power of n plus alpha 1 g. Okay, so that's your alpha Cg. So this is Ackermann's formula. So you can use this if you use MATLAB. You have a formula, you have a function to calculate. Okay, otherwise you can use this. This is the second method here. Okay, yeah. The third method, okay, I'll just touch upon the third one here is. So the third one is to make use of that control canonical form of the system matrix. Do you remember when we derived the discrete state space equation, we mentioned a couple of special forms, right? There's a control canonical, observable canonical, there's diagonal form. So here we're going to make use of the control canonical form. So suppose that the G, suppose the G matrix, this system matrix G, is in the control canonical form. Okay, so now probably the question you would ask is, so what if G is not in the control canonical form? Well, yeah, chances are it's not. So actually, yeah, what if G is not in control canonical? What would you do? Can you do something to transform that into a control canonical form, right? If you can, actually, what's the name for that? It's called similarity transformation, right? Yeah. So you can use similarity transformation to do that. So we use similarity transformation to transform the G matrix in the diagonal form. So you can, there is a technical approach to transform any basically matrix into a control canonical form. All right? Yeah. Okay. So suppose that it's in the control canonical form, and let's say suppose the G comes from. Suppose this is your basically original open loop or Planck transfer function. Okay. So this is maybe in general. Okay. So basically, the characteristic equation at here, or the numerator denominator here, is this guy here, right? It's this guy here. So if you transform this pulse transfer function into a discrete state space equation, and the control canonical form, the G, right? And you look at lecture notes, so this is basically our standard 0, 1, 0 up to 0 to here, 0, 0, 1. Okay. No, this is negative a in and here, negative a minus 1, and then up to a1 and here, a0, a1, yeah, and then on the top there's another 1 in here. Okay, so that's control canonical form, and H is 0, 0 up to 1. Yeah.
Don't you start having 1 in the first column?
Here?
Yeah.
No, there's no 1. There's already negative a in it here. Yeah. So okay. Yeah. So this is basically a sort of formula now. You can make use of this control canonical. This is the control canonical corresponding to this format of writing of this transfer function, right? Yeah. So I mean, this format of writing basically, I mean, I call this is A1, I call this is AN, right? If you look at different textbook, maybe the other textbook call this is AN and this is A naught or something like that. Okay, yeah. Okay, so this is control canonical, and what we want is, as we said, we want, right? We want our. Okay, so let's see. Just a second here. Yeah, before we write down what we want, if I write this characteristic equation, or the Zi minus G, which is determinant of this one here, that's basically the denominator right here. Okay. Yeah. A1. Actually, it's Z in it here. So this is the characteristic equation. So the reason I'm writing this one here, basically, I want you to understand right now, the A1 up to AN, right? This is known at here, okay? This is known because you have the system matrix G, and you will be able to have the numbers A1 up to the AN values here. Okay? So now we're picking up a K matrix, okay? Gain matrix. K, and the reason to get the K is such that we have the feedback. So let's see, the K matrix is K1 up to Kn. Okay, so then with the feedback, the system becomes G minus HK. Right, with the feedback. So basically, with with u equal to negative k, you plug it over here, and you get x of k plus 1 equal to g minus hk x of k, right? Yeah. Was that clear? Yeah. So this g minus hk, if I have the g at here, which is in the control canonical form, and we have the general k, which is what we're looking for. But if you plug this g minus hk, do a calculation, you'll see that this is in the form as 0, 1, 0, okay, up to 0 here. So actually, this whole portion right here didn't change at all, okay? So that whole portion didn't change. So what's changed? Only it's the last row at here. Only the last row changed. And the last row becomes negative alpha, not alpha, an plus kn, negative an minus 1 plus kn minus 1, and up to, okay, negative a1 plus k1. Okay, yeah. So this is not quite aligned here, but you know what I'm saying. So if you do a simple just algebraic calculation, you know, this matrix minus the k multiplied by h, okay, because h here is all 0 and there's only 1 in it here. So this is the reason there's nothing changed on the first n minus 1 row. Only the last row at here is changed here. All right? Yeah. So that's g minus hk. This is g minus hk. So then the closed loop characteristic equation is what? Zi minus g minus hk determinant, right? So this is the closed loop characteristic equation. And because of this special appearance or special form at here, okay? Because it's special form, when you use that I minus this and then calculate the determinant of this one at here, and it's all 0 at here, it turned out that this polynomial or this characteristic equation, which is the closed loop one, is z to the power of n plus a1 plus k1 zn minus 1, and keep going until an minus 1 kn minus 1 z plus an plus kn. Okay. Is that okay? Yeah. So it's probably hard to see. You say, oh, why is that? Well, you can practice. You can use a very simple 2x2 or 3x3 matrix to practice this one here. Because of this all 0 and 1 here, right? When you calculate the determinant, what you do is we call that either you have a column expansion or row expansion, and then you calculate the determinant of the submatrix, right? So you'll see that basically that's your closed loop characteristic equation. And this is only works, okay, this is only true when the G matrix in the control canonical form here, alright? Yeah. Okay, so then up to this stage, right, we show that with the control canonical form, the closed loop characteristic equation is in this form here. But what do we want, right? We want our closed loop characteristic equation to be the desired one. So what's the desired again? The desired is alpha c z equal what? Zn plus alpha 1 right. This is what we want, right? This is desired, and desired one is derived based on desired pole locations. So here's a desired. Here is the actuals, right? The actual ones based on the K1, K2, Kn. So which means if I want this to be the same as this, then what shall we do? We just have to compare each one of the coefficients here, right? each one of the coefficients. So that basically means K1 equal to what? Alpha 1 minus A1. And then up to Kn minus 1 equal to alpha n minus 1 minus An minus 1. And then Kn equal to alpha n minus An. See that? So this is basically the advantage or the benefits of this control canonical form at here. Alright? Yeah. So if your G matrix is in the control canonical, then the gain matrix K1 to Kn can be easily calculated based on the desired polynomial like this. Was it clear? Yeah. So of course the $1 million here question is, how do you convert a G into a control canonical, right, to facilitate this easy of a calculation at here, right? Okay, so that's a little part of the optional in my lecture notes here. Actually, how would you convert the G matrix, regular G matrix, into a control canonical form there? All right, yeah. So maybe I'll just roughly write down here. So what you do is you can use similarity transformation. So you define a T matrix which is M by W. Okay. This M here is the controllability matrix. So M is the controllability matrix. Okay, so M is a controllability matrix, and the W is a sort of special matrix which is formed by the coefficients of this A1 to AN at here. Okay, so the coefficients of this open loop or the plant transfer function. So here's AW. This is W here. A minus 1, A minus 2, A1, and 1 in here. And An minus 2, An minus 3, and then 1 in here. And then down to A1, 1, 1, 0, 0, 0, 0, 0. Okay. So this is the W at here. Alright? And this T matrix is what we can use to do this similarity transformation. So we can show that this T inverse GT, okay, this T inverse GT will give control canonical form. Okay, we'll give this control canonical. So that's kind of in short at here. So how is that possible? You can take a look at the lecture notes as to the detailed proof here, right? Yeah. Was that okay? So those basically, these are kind of 3 different approach you can do pole placement, right? These 3 different approaches is kind of give you different ways of doing hand calculation here, right? Different hand calculation. So which one is better? It's really hard to say, yeah. But when you do simulation, it doesn't make any difference at all, right? Yeah. So you basically you just use a command to do it. Yeah. So the only purpose out of here is actually just kind of to deliver the mathematics behind the usage of regular commands, right? Yeah. Okay. So far the pole placement at here, what we learned, right? Remember what I called it? I called it regulator. Okay, basically you don't have a reference control. You're only regulating your initial condition back to 0 with this feedback here, right? Yeah, so that's a regulator. So, but more often in control is we control the system when there is a reference input. The reference input can be a unit step input or can be a sinusoidal input, right? Yeah. So the next question is, let's look at the control system with reference input. With the reference input, that basically means you have R over here. Okay. So I'll purposely leave a little block at here. Okay. Yeah. So there's a reference input, and then you have this plant at here, and the plant, okay, is in whatever format, state space or transfunction. Then we have a negative feedback, and so this is x of k at here. Okay. Then the x of k multiplied by c will give us y of k. The negative feedback works on the x of k here. Okay. So this portion, right, if there's no reference input, this portion is what we just covered here, right? You know, regulator. So now if I have a reference input into this loop at here, so this is basically become a control system with reference input. Then in this particular case, we're going to add, okay, an additional gain at here. Let's call it K naught. Okay, additional gain here. So this K naught will work with this reference input R. Right? Yeah. So now here's this diagram. Now then, what will be this mathematics behind here? So this x of k plus 1 equal to gx of k plus u of k. So that's still your plant. It's not going to change. Okay, so this is still your plant. And y equal to cx of k. Okay. Yeah. So now the only difference is this u at here. So the u is the input at here to the plant. So if you look at the u, it actually becomes what? Negative k multiplied by x of k, and then plus k naught multiplied by r. Okay, so let's call this is discrete. So let's call this is r of k at here. Okay, so k naught r of k. So this is your u of k now, right? With the reference input, we have this guy here. Okay, and this. Is that clear? Yeah. Okay. So this k, this k at here, okay, so it's different from this k now because this is actually a vector. This is the n 1 by n for a single input, single output system, because this is just 1 by 1 in here, right? So the k naught at here is actually just a scalar value. Okay. Yeah. So that's just going to be a scalar here. Then what will be the closed loop system now? So if we substitute this u of k back over here, okay, substitute back here, then the closed loop becomes g minus hk x of k plus hk naught r of k. Okay, so this is your closed loop one now. So now the purpose of this k and k naught will be this. So this k should be selected, okay, to have desired, okay, closed loop characteristics. Okay. So the K needs to be selected to have a closed loop characteristics. Essentially, the key here should be selected the same fashion or manner as the previous regulator. Okay, you have a desired poles, right? What decide on the desired closed loop characteristic is the desired pole location, right? So the key should be selected such that you have the desired closed loop here. And this K naught, okay, the K naught should be selected such that the output Y follows the reference input R. Follows not necessarily means just follow. Follows actually means precisely to catch that guy, right? To be the same. Okay? So here's basically the idea now. If your input is a unit step input and you want your output to be the same, to reach the same value as the reference input, then what will be the DC gain of the system? We learned the concept DC gain. You actually did one of the assignments. You want your output value to have the same value as the reference input. What will be the DC gain?
1.
Yeah, 1, right? So the DC gain needs to be 1. If DC gain needs to be 1, so which means actually the K naught should be selected such that DC gain is 1. Okay? So basically we need to select the K naught such that DC gain of the closed loop system is 1. Then we can guarantee that Y of K eventually will reach this R of K. So this basically means Y of infinite will equal, well, not exactly 1, but so which means this is going to be 1 if R of K is U of unit step. Yeah. Okay, so let's take a look at an example here, okay, as to how would you derive and combine those relationships in here. So let's say my G matrix is 0, 1 of this, and H this, okay, yeah. So here is the system matrix, and now we're going to design a tracking system, right? So when you have this kind of control with the reference input, so what generally we'll see is this tracking problem. Okay, so you're tracking certain reference input. Okay, so then we'll do a little hand calculation in here, right? Yeah, you can easily figure out this controllability matrix. Okay, so this controllability matrix 0, 1, 1, -1, and here. Okay, and the rank of this controllability matrix turned out to be 2, so which means this is controllable. And if it's controllable, then it means we can place our poles anywhere we want. Okay. Yeah. So let's say we're gonna pick 2 poles, desired pole location. So I'm gonna pick the desired poles as this. Okay, 0.5 plus minus J 0.5. Then your desired characteristic equation, the alpha CZ, which is desired characteristic equation, is going to be Z minus Z1 multiplied by Z minus Z2, right? And that equal to what? Based on the desired pole location, that's Z minus 0.5 minus G 0.5 and Z minus 0.5 plus G, this, right? Like this. Okay. So multiply this thing out, okay, and you'll see that this is Z squared minus Z plus 0.5. Okay, so this is your desired polynomial or characteristic equation. And we need to pick our k, right? So we need to pick k such that z minus g, zi minus g minus hk. Okay, so basically here's a closed loop system matrix. The eigenvalue of the closed loop system matrix should match the desired polynomial here. Okay, so this guy should be the same as this. Okay, so this should be the same as this. Was that clear? Yeah. So you can use two different approaches here. You can use Ackermann formula. You can use that control canonical form. Okay. As a matter of fact, this this G matrix. Yeah. As a matter of fact, the G matrix that is here. Okay. This is already in the control canonical form. Okay. This is already in control canonical. If this is already in the control canonical, you actually can make use of what we derived here, right, to calculate K1 and up to K2. Okay, yeah. So, or you can use Ackermann formula. So I'm gonna maybe skip that to just a little bit here. So maybe I'll just try the Ackermann's formula here. Okay, try the Ackermann's formula. Ackermann formula k equal to 0, 1 at here, then multiplied by h, gh, inverse, then multiplied by alpha cg, so alpha c of z is over here, so alpha cg will be just plug the g into this matrix, into this polynomial. Okay, yeah. That's Ackermann's formula, right? Yeah. Okay, if this is Ackermann's formula, and then you can just simply do some simple matrix calculation. HGH, the controllability matrix, is this guy. So the inverse of this multiplied by this and that. So that K can be easily obtained. And this turned out to be 0.34, negative 2. That's your K matrix. Okay? Yeah. Okay, so if this is the K matrix, now let's go back to our original system and here. Then my original system, closed loop system, is xk plus 1 equal g minus hk, x of k at here, plus hk naught r of k, right? Yeah, so there's a little confusion. There's a lot of k's at here, right? So this this k is not this k though, huh? Yeah. So this is your closed loop system here, and we already got our K matrix K. We have G, we have H. So this G minus HK, let's call that G hat. Okay, let's call that G hat. Okay. So that can be calculated. And this is 0, 1, negative 0.5, and 1 at here. And this H K naught that needs to be decided. So this H K naught, let's call that H hat. Okay, let's call it H hat. So this is H K naught. And H is 0, 1. So basically that means what? This is 0 and K naught. Okay. Okay. Remember, how do we determine the K naught value? The guideline is to make the DC gain to be 1, right? Yeah. So in order to get the DC gain, so what we have to do is we have to move it back to this pulse transfer function. So we have to obtain the closed loop pulse transfer function, and then set DC gain equal to 1, find the K naught value. Okay? Yeah. So what's the closed loop pulse transfer function, PTF, right? Closed loop pulse transfer function. So basically you're looking for is what is the pulse transfer function between the output Y and the input R. Okay? Yeah. Now here is the closed loop system at here, right? Here's a closed loop system. Where's the Y? Y is Y of K equal to Cx of K at here, right? This is Y. Okay? So technically what you can do is just you can take Z transform of both sides of this equation, Z transform both sides of this equation, and then do some simplifications to find the ratio between Y of Z and R of Z. Okay? Yeah, so that's what technically what you can do basically. But actually you can also make use of the formula. Remember the formula we said, what's the pulse transfer function for gx over here plus h u and y equal to cx of k. Remember, what's the pulse transfer function for this guy here is what? It's y of z over u of z equal to c zi minus g inverse and then h, right? That's basically, we derive this one here. The pulse transfer function for the open loop is this guy here. Okay, it's this guy. So now if you do a little comparison at here, this is your G hat, right? This is G hat. This is H hat. And this R at here, right? This R here basically is a comparison to the U over there. You see that, right? Yeah. This H hat is the H hat here. This G hat is the G over here. So technically you can make use of formula. So the pulse transfer function for this closed loop system is what? C zi minus G hat. Okay, and inverse. And then multiplied by H hat. Okay, so that's the pulse transfer function of the closed loop system. We have this we have the G hat, okay, and we have the K naught here. So you need to do a little symbolic calculation. Keep the K naught as unknown here. So that's gonna give you this K naught over Z squared minus Z plus 0.5. Okay, it's gonna give you this. Does that make sense? If you look at this denominator here, what is that denominator? That's basically what? The desired characteristic equation, right? Yeah, which has a pole of 0.5 plus minus J 0.5. Okay? Yeah. So your closed loop system, it's exactly what we want, except the K naught is still an unknown value here. So the last step is we need the DC gain to be 1. So DC gain to be 1 meaning DC gain meaning what? Meaning the pulse transfer function at here, okay, at z equal to 1 needs to be 1. So this k naught z squared minus z plus 0.5 at z equal to 1, okay, yeah, needs to be 1. Okay, that's a DC gain for a discrete system, okay? Yeah. So if you plug z equal to 1 into here, you get 2k naught equal to 1. So k naught equal to 0.5. Okay, so that's kind of the general procedure of deriving this k naught. Okay, when it comes to reference control or tracking control at here, right? Yeah. Was that clear? Yeah. So if you do a little simulation at here, let me see. Do I have a simulation? Maybe I don't have a simulation. Okay, so I don't have a simulation. So maybe you can do a simulation at here, right? So just simulate this system with the k's and k naught with the reference input, and just check if you have a desired output with a 0 steady state error. Okay? Yeah. So try some simulations here. You can simulate either using Simulink or you can use script file. It's just fine. Okay. Another controller I want to talk about today is called Deadbeat Controller. Okay, Deadbeat Control. Or something we call Deadbeat Response Control. Okay. Now this kind of control, you can only see this kind of control in digital control system. Okay, it doesn't exist in continuous system. All right, yeah. So what is a deadbeat control? Okay, so deadbeat basically means the response of the system, control system, is very fast. And here is your original system. Okay. And now we have this feedback. Okay, so that gives us this closed loop bin. So I'm just kind of rewriting it here of this, right? Give us the closed loop of this. Okay. Now we know that the solution of this one, right? The solution of this. What's a solution? Basically means the solution of this is g minus hk to the power of k x of 0. Okay, so that's your solution. And this is basically well, we talk about this when we derive the so-called state transition matrix, right? Yeah, this is a solution here. Now, if you look at the solution at here, how fast the response is going to be depends on what? Depends on the eigenvalues of this matrix, right? Basically, depends on the closed loop poles location. Okay, yeah. And that's the whole idea of pole placement, right? Okay, so the closer of the pole location to the origin, then the faster response is going to be, right? Faster response is going to be. Then here is basically saying that how about if we place the pole of the system to be exactly at the origin, right? Yeah. So if that's the case, then basically we're expecting a fairly fast response, right? So basically, let's see what we do. We place the poles at origin. Okay, at origin here. If the origin, basically, the eigenvalue of this one is going to be 0. Okay, going to be 0. If this is the case, that means this zi minus g minus hk, okay, will simply, what will be the polynomial now, or what will be the desired polynomial? if you place all the desired poles at the origin, the desired polynomial would simply become this, right? So all the other coefficient alpha 1 and 2 and 3, right, they're all going to be 0. Right? So this becomes your desired polynomial here. And this is basically so-called deadbeat control. Okay, deadbeat control. Yeah. Technically, theoretically, what happens is when you do this deadbeat control, okay, it's possible that you can bring your control. Okay, you can bring this x of k, okay, back to 0 in at most n number of samples. Okay, so basically, what this means is, okay, technically, here's a regulator here, right? Yeah. So you can bring this x of k, okay, to 0 okay, in at most n samples. Go. So if one sample is 1t, if the all system order is 2, so you can actually bring that back to 0 in at most 2 sampling times. Okay, yeah. So that's basically deadbeat control. Is that good? So if I give you an example right here, okay, and I don't think I'm going to write that example now. This is basically an example we did in the double integrator. So I'll show you in the lecture notes here, okay, just to save us a little bit of time here, because the theory is very simple. Okay, so this is what I did here. Okay, so remember in the previous lecture we derived a certain system gain matrix for a double integrator, right? Pole placement. Okay. So with the K1 and K2 as this, we can place our pole P1, P2 is a coefficient of the desired polynomial. So we can place, we can select K1, K2 based on the desired coefficients in here, right? Yeah. If we're designing deadbeat controller, basically means P1, P2 will be 0. Right. So the K1, K2 essentially becomes a function just sampling time t, right? Sampling time t here. Okay, that's k. Given different sampling time t, you have a different k values, right? And the deadbeat controller, you put it in the closed loop system, will be this one here. Okay, will be this. So here's a little hand calculation in here. If initially it's 1 and 1, basically there are two non-zero initial value. And for the first step, t equal to 1, your x of 1 equal to this. I don't know what to count here. Your x of 2 equal to this. So x2 is actually already 0 at here already, right? x2 is 0. Okay? So that's the first step, right? If you take a second step, you'll see that oh, sorry. Yeah, this is the first step here, and this is the second step here, right? This is your first step, this is your second step. So at k equal to 1, your initial is 1, 1, and it's still this. And at k equal to 2, it's already coming back to the 0, right? So that's basically deadbeat. At most 2 steps, right? So n number of steps, okay, or sample times. Yeah. So the only catch, right? The only catch is this. If you relook at the control input, okay, the U, as a sort of a comparison to the sampling time t at here, okay, because you're trying to basically do a deadbeat control at here, right? Deadbeat control. See what happens when t equal to 10 seconds, U is still good. 1 second sampling time is still good. But when t is 0.1 second, the U becomes extremely large number at here, right? Extremely. So that's basically the compromise when you do deadbeat control. You want it to have a fast response, that means the U actually needs to be very fast, your control voltage into the system, right? In certain situation, this is not going to be feasible. So you don't have your motor probably only positive negative 5 volts, right? You don't have this high inputs here, so you won't be able to reach your desired deadbeat. Okay, yeah. But theoretically, it can be realized for the deadbeat control, right? So if you take a look at the response set here, okay, and in 2 steps basically, and this is a simulation of a reference input, just a little modification when it comes to the reference input. Okay. So try this out. Okay, so let's play around with this with the code here, okay, to get some feelings about this pole placement and the deadbeat control. Okay. Deadbeat control can also be realized in pulse transformation, basically using Z transformation. So if we got time, we'll talk about that maybe in the future. But for now, okay, this is a deadbeat control in state space here, okay, using state space method. Okay. Any questions? Yeah, we're good. Okay, so that's sort of finish this pole placement control right here now. Okay. And now let's talk about the next one here. Basically, we're going to temporarily moving back from state space back to the Z domain there. Okay, yeah. So basically, then we talk about the mapping. Okay, from S to Z. Okay, so we'll gain a little bit more vision into this mapping from S to Z. Okay, and particularly in terms of the response to the post location. Okay. And come back to the very basic. Okay, here's a signal, here's a sampling. So okay, here's sampling. Or here is X of S. Here's X of Z. Right? And you have the Z table. Basically, you have some very common conversions from X of S to X of Z. So actually, this basically means from X of S to X of T first, then to X of K, then to capital X of Z, right? Yeah. So that's what we learned. And some of the very basic ones, if you have a 1 over S plus B, okay, if this is your X of S, basically that represents in time domain, it's e to the power of a negative bt. Then you do a sampling. Okay, so e to the power negative bkt. The corresponding Z transform. So over here, I'll simplify that a little bit here. I'll just write it as okay, a to the power of k. So what's a value? So the a is e to the power negative bt. Okay. Okay? Yeah. Then the Z transform of this one is a Z over Z minus A. Right? Z over Z minus A. Okay. So just kind of jog your mind in here. So what this basically means is okay. So there's a little comparison at here, and this is exponentially decay at here, right, if b is a positive value. Okay, and here this is exponential decay, something like this, right? Yeah, and then after sampling, you should have, you know, something like that, right? Yeah. So you can tell this exponential decay from here, but over here, what can you tell? Now basically you can tell that by the value of a here, right? The value of a. If a is a positive and less than 1, then you have this exponential decay here. Okay, yeah. Good. Okay, so that's pretty basic here. Yeah. Now, what about complex number here? Okay. So let's take a look at the complex. So let's call this is case number 1, case A here, case 1. So let's look at the case number 2 at here. Okay. So let's say suppose I have a complex conjugate roots. A complex conjugate roots. So sigma and omega, let's say, is supposed to be omega is greater than 0, sigma maybe greater than 0. So this is basically a denominator. If you set the denominator equals 0, you have two complex conjugates here, right? Yeah. And you will see that in the continuous system of time domain, this represent e to the power sigma t and sine omega t at here. Okay. If you sample this, it becomes sigma kt sine omega kt. Okay, yeah. So bear with me about this. You probably see what's the point of doing this. So I'll tell you what the point of doing this. Okay, just shortly. So you sample this, you get this. Then if you do a Z transform of this one in here, right? If you look at your table, you have this Z transform in your table. You will have, okay, this is E sigma t sine omega t z over z squared minus 2e sigma t cosine omega t z plus e2 sigma t. Okay, so you get this. Okay, yeah. Now if I do a similar things, if I let e to the power of sigma t, okay, to be a, okay, if we let this e to the power of sigma t to be a, so this guy is a at here, okay, then this guy will become just a sine omega t z over z squared minus 2a cosine omega t z plus a squared, okay, plus a squared. Okay. So what is the pole at here? The pole at here is S equal to sigma plus minus j omega, right? That's the pole at here. After this transformation, okay, after this conversion from S to the Z at here, coming back here now, right? Coming back here. So what will be the pole's location at here now? So the pole at here, what do? You basically you set the denominator equal to 0 and you solve for the Z, right? Solve for the Z. So you'll see that the pole at here is Z12 equal to a cosine omega t plus minus j sine omega t. Okay, sine omega t. Yeah, just set equal to 0, solve, and you'll get this, right? It's quite simple. Now, for this one here, that's what? What's A? A is this, right? A is this. E sigma t. And what's this guy here? That's what? Ej positive minus j omega t, capital T. Okay. And if I combine these two together, that's what? Sigma plus minus j omega capital T here, right? Okay, so we're getting there. So the whole purpose of doing this is the pole at here is mapped to here. What is the mapping formula? It's what? Right? Yeah. So maybe I shouldn't even just do this, as because that's kind of fact we learn, right? Yeah. So basically, the pole, when you do a Z transform, right? When you basically sampling a certain continuous time signal, and then you do a Z transform, then the pole describing the characteristic of the continuous signal is gonna be mapped using this relationship at here. Is that clear? Okay, good. So learn this fact now, and then what I'm gonna do, make use the rest time is let's observe a few things at here. Okay, just to get ready for the next lecture. So just kind of seconds at here. Yeah. Okay. So if you let me use one example, one of the assignments that you did here. Okay. In one of the assignments, I was asking you is this. So if you remember, this is one of the assignments that can you calculate the inverse Z transform of this one here, right? Calculate the inverse of Z transform. And I think you did that Z transform, but basically for this particular one here, this has a pair of conjugate roots set here. Okay, so your P1, P2 or Z1, 2 is 0.4 plus minus 0.4 and root 3 by J. Okay, so that's Z1, 2 at here. Okay. Okay, so if this is A plus JB format here, right? If I write it into R and theta, okay, format, this is a complex conjugate root. So I can write it using R theta format. It's going to be 0.8 angle positive minus pi over 3. Okay, it's going to be this. So R equal to 0.8. Theta equal to pi over 3. Okay, theta equal to pi over 3. Now, what is the inverse of this guy here? If you see that the inverse of this one here is going to be 0.8 to the power k cosine pi over 3k plus 1.4 root 3, then 0.8k sine pi over 3k, like this. Okay, like this. Okay. Now, from basic trigonometry and or system point of view, okay, so there's cosine and sine, both of them having the same pi over 3 at here. So you can combine these two together. Okay, combine them together. When you combine them together, okay, there's a value here, and this is going to be cosine pi over 3k and plus certain phase at here. Okay, plus a certain phase. Was that all right? Yeah. Okay, so now the next thing what I'm going to try to illustrate is what is the effect of this 0.8 and what is the effect of the theta value pi over 3 on the response of y of k. Was that okay? So basically, you see here, this is R is 0.8. And in the response of y of k, the r and theta are the pole locations here, okay? Based on the pole's location. And the response of the y of k is actually directly related to this point 8 for the r and what? Theta, right? And theta here. So it's actually a little bit easy to understand for the r here, which means the r value depends on what? Depends on, the r value decides what? Decides on the, if it's smaller r, then what happened to y of k? If it's bigger r, then what happened to y of k? Yeah, right? So the smaller the r is, the faster response of this k here, right? Basically, it'll decay faster, basically. Okay. What about the theta here, basically, right? What would the theta here decide on here? Now, the other thing is, what is the theta, right? What's the theta here? If you look at this one, if you look at what I just derived here, what's the theta? Theta is basically what? This one. The omega t, the omega capital T there, right? Omega capital T. So now let me use sort of just a standalone cosine here just to illustrate the effect of the theta. Okay, I see it here. Let's say I have a cosine. Let's say we have a certain, let's say, cosine, maybe pi over 8 t. Okay, let's say suppose I have a cosine continuous signal right here. Okay, continuous signal, and now we're going to sample this one here. Okay, we're going to sample this one. So if I sample this one, it'll become what? Cosine pi over 8, then capital T multiplied by k. Okay, right? Or if I write a k capital T, that's fine. Just kind of reverse order here. Right, so I sampled it using a sampling time capital T. Now, if you look at this one here, now let's examine this. Basically what happens is this pi over 8 is what? Is omega, right? It's omega. That's the frequency of your original time function. Now after sampling this pi over 8 by t, that's what we call, this is a theta. Okay? So let's call this is omega n here. Okay? Your natural frequency of the previous original one here. After sampling, this is a theta here, right? This theta here. So what happens if I set this capital T to different values? So let's choose a t equal to 1, 2, 4, and 8. Okay, so if I choose different t values at here, right? Different t values. Let's see what happens. And this is basically the graph at here, right? So when t equal to 1, okay, your theta is pi over 8. Was right? Yeah. See, theta t equal to 1, theta is pi over 8, right? So here is the response. When t equal to 2, your theta is pi over 4. When t equal to 4, theta is pi over 2. When t is 8, theta is pi. Okay? Yeah. Okay, so look at the response here, right? Now tell me which one has higher frequency. Which one do you think has higher frequency? Hmm? And why? Which one?
T equals 1.
This one, right? Yeah. Why this one has higher frequency? Because up, down, up, down, up, and down, you know, right? Yeah. That's the highest that's the frequency. That's basically oscillations here, right? That's oscillation. Right? So what's the theta value here? It's pi. So basically, the theta value determines what? The oscillation, okay? The frequency. But this theta, you got to be careful. This theta is not a continuous one here, okay? So we're talking about the frequency of a discrete signal. So we're talking about the frequency of discrete signal. Okay, this is not the frequency of your continuous signal. Okay, yeah. So the next question is, do you think you can have a higher frequency than this one? Not at all, right? So this is the basic high frequency, up and downs here, right? This highest frequency. So theta equal to pi represents the highest frequency. Or what? Or theta is negative pi, right? Or theta is negative pi. Okay. So coming back here, with the sampling, R determines how fast the response is going to be. And theta at here will determine what? The oscillation. What kind of oscillation would you see in the discrete signal here? So this is your discrete signal here, right? This is a discrete signal. Guess what? If this theta is not pi over 3, if this theta is pi here, then you're actually going to experience 0.8, negative 0.8, 0.8, negative 0.8, that kind of situation, right? Yeah. So this theta determines basically the oscillation in the discrete signal. Okay, yeah. So I'm writing on here. So R, okay, decides on, okay, on the response speed, and the theta, okay, decides on the oscillation, okay, of the response. So you may not have oscillation. You know, basically, you may not have oscillation. You may have you know, essentially like this. There's no oscillations at all. Okay, yeah. You may have oscillation. Okay, or you may have oscillation like this. Okay, you may have oscillation like this. So that all depends on the theta value. So what is R and theta then? Let's come back and examine this slide a little bit more careful here. Here is your closed loop system pole, sigma plus minus G omega. Okay, so here is S is sigma plus minus G omega. And it's going to be mapped into Z domain or Z plane with this equation, which is e to the power sigma t, e to the power positive negative G omega t, right? Okay. So what's R and theta at here? So basically, this is your R, and that's your theta here. The omega t, okay? The omega t give us the theta, okay? Give it the theta. So this is basically all about the next lecture, the mapping. We're going to look at closely looking at the mapping here. Okay, so for different kind of losses, okay, in the S plane, where is it going to be mapped to in the Z plane? Okay, what's the relation? Basically, what's the connection there? You know, how's the mapping here? You know, lossy basically means, for example, we are talking about maybe the left-hand plane. That's stable plane, right? Maybe you have a pole, okay, or along this line at here, right? Along this line. So what's along this line here? Anywhere along this line basically means the omega value. This is omega axis, right? Omega axis. So anywhere along here, that means you have a constant omega value, right? So that's kind of what we call lossy. Okay, or maybe we're talking about lossy like this. So that means we have a constant what? Sigma value here, right? Yeah. So how's that mapping from those loci to the Z plane? What kind of a curve will look like in the Z plane, when you map that from S plane to a Z plane. Okay, to a Z plane. So that's basically what we're going to talk about next lecture. Okay. Okay, so any questions? We're good? Okay. So no lecture next week, and it's a reading break, supposed to be. If you are feeling behind, I think this is time to catch up. Okay, I'll make sure all the lecture notes are on the blackboard. And also don't forget assignments. Oh, the project, right? Yeah, the project.